Do you think gravity is pulling you down? Absolutely wrong. In reality, the ground is rushing up and slamming into your feet.
And here are 9 reasons why, as demonstrated by Nobel Prize-winning theoretical physicist Richard Feynman.
1. The hoax of the century. Gravity is not a force. You probably think you understand gravity, right? Try stepping onto a bathroom scale. Look at the number displayed there. That's your body weight. The Earth is pulling you downward. Everything seems incredibly simple. Drop something, and it falls to the ground instantly. The moon orbits our Earth. The planets orbit the bright sun. Objects with mass attract one another. Newton figured this out centuries ago. The so-called gravitational force seems straightforward, surprisingly simple even. But that is completely wrong. And not just a tiny bit wrong, it's fundamentally incorrect about what's actually happening.
Because gravity is absolutely not a force as we conceive it.
And once you see gravity's true nature, the universe changes. Let me show you right now. Try to stand up this very moment. Feel the weight of your own body. What are you feeling? You'd say that's gravity acting on you, that the Earth is pulling you downward. But think about that actual sensation. The floor pushing into your feet, pushing up. That's the real feeling. That's the floor pushing you upward. That mysterious pulling force everyone talks about, you've never felt it. You only feel the push, always upward, never downward pull. So where is that pulling force located? And here's something even stranger. The moon is falling toward the Earth right now. It's been falling like that for billions of years. Yet it never gets any closer. It just circles. Always falling, but never hitting the ground. What kind of pulling force works like that? A pull that lasts forever, but never manages to attract anything inward. And according to Newton, that pull happens instantaneously. Move the Earth, and the moon feels it instantly, across 240,000 miles of vacuum, right away. How can that possibly happen? What carries that message so far? What is the actual mechanism at work? Even Newton couldn't explain this phenomenon. He called it action at a distance, and admitted he didn't understand how it worked. But the math was incredibly beautiful. The predictions were absolutely perfect. So people stopped asking those nagging questions. They really shouldn't have stopped. 2. When a tiny error changes the course of history. Let's go back a few centuries. No one understood how the planets moved. Copernicus said they circled the sun. That was fine, sure. But in what way? What paths did they follow in the sky? Tycho Brahe built an astronomical observatory and spent decades recording the positions of the planets, night after night, year after year, measuring angles with precise brass instruments down to tiny degrees. Why did he have to be so accurate? Because you can't understand nature by guessing. You have to look very closely. You must measure carefully and in detail. Record exactly what you see. That is where real science begins. His data later reached Johannes Kepler. Kepler wanted to find the shape of the planetary orbits. He tried circles first. The predictions were close enough, but Mars was off by 8 arc minutes. That's 8/60ths of an angular degree. Most people would have dismissed that as a measurement error, but Kepler knew Tycho Brahe's precision. That man did not make an error of 8 arc minutes. So Kepler discarded the old theory and started over. After years of work, he found it. They were beautiful ellipses. Planets follow ellipses with the sun at one focus. It matched the collected data perfectly. How elegant that was. But it raised a bigger question. Why ellipses? Meanwhile, Galileo was conducting simple experiments, rolling balls down inclined ramps. Sounds trivial, right? But observe what happens. Roll a ball down a slope, and it will accelerate. Roll it on a flat surface, and it keeps going, not stopping immediately. Imagine you could eliminate all friction. What would happen? the ball would roll forever. Same speed, same direction, forever. This thoroughly confused people. Surely motion requires a constant push. Surely everything naturally comes to a stop. No, that thinking is totally backward. Motion is the most natural state. An object moving in a straight line doesn't require explanation. That's the default. What needs explaining is the change. Slowing down, that's caused by friction. Speeding up, that's due to some push. Changing direction, that's a sideways force. This is inertia, the first law of motion, and it creates a serious puzzle. Planets should be moving in perfectly straight lines. That is their inherent natural state, but they aren't doing that. They are following continuous curved paths. Their path is constantly bending toward the sun. Something is deflecting them every single moment. What is that? 3. Newton and the era of universal gravitation. Sir Isaac Newton saw that very clearly. Planets want to go straight. That's their inertia. But they are constantly bending their path. Something is continuously changing their motion. He called that force gravity, the universal attraction between any two masses. The force depends on mass and the object's distance. Greater mass means a stronger force. Greater distance means a weaker force. Specifically, the force decreases by the square of the distance. With this principle, everything falls into its proper place. Why ellipses? Because the planet is falling towards the sun while moving sideways. This combination creates elliptical orbits. Kepler's laws arise naturally from Newton's force law. Why does the moon orbit the Earth? It operates by the very same principle. It falls toward the Earth, but moves sideways fast enough to miss. It falls around the Earth instead of into it. Why does an apple fall to the ground? The Earth is tugging on it. Same force, same law, just a different scale. Newton performed a stunning calculation. He calculated how much the moon falls, how much it deflects every second. Then, he calculated how much objects fall on the surface of the Earth. The numbers matched perfectly when factoring in the distance. It was a major revolution. The force pulling the apple was the same force holding the moon. Heaven and earth, governed by the same physics. With Newton's laws, everything made sense. Tides occurred because the moon pulled the oceans. The Earth is round, but bulges at the equator because it spins. Comets returned on schedule because they follow elliptical orbits. Strange observations found explanations. Jupiter's moons sometimes arrived early, sometimes late. It turned out light needed time to travel. When Earth was farther from Jupiter, the light took longer. This led to the first measurement of the speed of light. Planets wobbled because they pulled on each other. From the wobble of Uranus, they predicted a new planet and found Neptune exactly where predicted. For 2 centuries, Newton's law was a great achievement. It explained everything anyone could measure. 4. The mystery. Why do a hammer and a feather fall equally? Drop a hammer and a feather in a vacuum. They hit the ground at the exact same moment. Exactly together. The hammer has far more mass than the feather. According to Newton, gravity must pull it harder, many, many times harder. But the hammer also has far greater inertia. It resists acceleration more than the feather does. Many, many times more. These two effects cancel each other out perfectly. Not just approximately canceling out, but absolutely, perfectly, perfectly. All objects fall at the same speed regardless of their mass. Why is that the case? Newton's theory required 2 different properties of mass. Gravitational mass determines how strongly they attract each other. Inertial mass determines how hard it is to accelerate them. And these 2 properties are always perfectly proportional. With astonishing accuracy. Why are the property of attraction and the resistance to acceleration equal? Newton had absolutely no answer.
Was it just a random coincidence that made the math beautiful? Or was it not a coincidence? Einstein posed a completely different question. What if it wasn't random? What if that equality revealed something about the nature of gravity? 5. Einstein bends space to find the truth. Here is a thought experiment for you. You're inside a windowless, sealed room. You feel your normal weight. Are you on Earth or inside a rocket ship accelerating in deep space? Can you tell the difference? Drop something and it falls to the floor in both cases. Throw a ball horizontally. A curve appears in both cases. Step on a scale. The reading is the same in both cases. No experiment can distinguish between them. This is the famous equivalence principle. If you cannot distinguish gravity and acceleration, perhaps they are one. Perhaps sitting still in a gravitational field is actually acceleration. This was Einstein's great revolution. Objects in free fall have no force acting upon them. The falling apple, the moon, satellites, floating astronauts, none of them are subject to any force. They are moving naturally along their natural paths. No force, no pull, no thing affecting them at all. But the apple is clearly falling, isn't it? Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path and space itself is curved? This was Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Large objects don't pull other objects in. They curve the space around them. They warp, bend, and distort the geometry. The apple isn't being pulled toward the ground. It's following the straightest path through curved space-time. But space-time near Earth is curved, so straight points toward the center. You standing on the ground are not being pulled down. You are trying to follow the natural path through curved space-time. But the ground is blocking you away. The ground pushes you up, preventing you from following the natural path. That is what you feel as your weight. It's not gravity pulling down. It's the ground pushing up, deflecting you from your natural trajectory through curved space-time. 6. When light bends, the truth is revealed. Einstein made a very specific prediction. If gravity is curved space-time, light would also be affected. Light has no mass in Newton's theory. Gravity should not affect light at all. But if gravity is curvature, passing light would be bent. During an eclipse, astronomers measured the positions of stars. The stars appeared shifted from their true positions. The starlight had been bent passing near the sun. This is the phenomenon of gravitational lensing today. We see this in routine observations now. Large objects bend light from more distant ones, creating distorted images. Direct proof that space itself curves when mass is present. Astronauts in orbit look weightless. They just float around like that. No gravity up there, right? Absolutely wrong. The gravitational field at satellite altitude is almost as strong as on the ground. It's about 90% as strong as it is down here. So why are astronauts floating? Because they are actually falling. The entire spacecraft is also falling. Everything is continuously falling toward the Earth. But they are also moving sideways very quickly, about 17,000 miles per hour. As they fall, the curved surface of the Earth falls away beneath them. They just keep slipping past. They fall around the Earth instead of into it. Everything is falling at exactly the same rate, so there is no sensation of falling. No weight, no sense of up or down. The sensation is identical to floating in empty space. This is the equivalence in action. Free fall feels exactly like floating because they are one. When in free fall, no force acts upon you. You are following the natural geometry of curved space-time. 7. Cosmic geometry. Why is the Earth round? Think about the surface of the Earth. It is obviously curved,
But standing on it, it looks flat to you. And here is something even more remarkable. Why is the Earth round in the first place? It's caused by gravity, but not in the way you usually think. Not a force pulling everything toward the center, kneading the Earth into a sphere. Instead, space-time around the Earth curves equally in every direction. Every rock and droplet of water tries to take the straightest path through that curved geometry. And when everything follows that curve equally, you get a sphere. The only shape where all points on the surface are equidistant from the center. The Earth is round because that is the result when matter follows curved space-time. The shape naturally emerges from the geometry. An ant walking what it thinks is a straight path is actually going on a curve. But from the ant's perspective, it's going perfectly straight. That's what happens to everything near Earth. Except it's not just space that curves, it's space-time. It's space and time together. Space-time. Large objects create curves in space-time, dips, wells, distortions. The sun creates a very deep well. The Earth creates a slightly smaller one. Even you create a tiny well. Too small to measure easily, but it is there. Objects moving near these wells naturally follow a curve. Not because they are pulled, but because they are taking the straightest path through curved geometry. The moon orbits the Earth because it follows the natural geometry of curved space. That geometry turns the straightest path into a circle. The apple falls because it follows the curved space-time near the ground. In that geometry, moving straight through time means heading toward the center. When you throw a ball, it follows a parabola. It's not because gravity is pulling it down. It's because it's moving through curved space-time, and a straight line looks like a curve. You are standing upright right now. You will feel your weight. In Newton's picture, gravity pulls down, and the floor pushes up. Two forces in balance. In Einstein's picture, only one force acts upon you. That is the floor pushing you up. But if there is only one force, you must be accelerating. And you absolutely are. You are continuously accelerating upward. The natural path through space-time heads toward the Earth's center. That is the natural free-fall trajectory. But the floor is blocking your way. It pushes you up, deflecting you from the natural path. You are like a person standing inside an accelerating rocket. The floor pushes and you feel your weight. Not from any downward pull, but from being accelerated away from the natural path. The apple hanging on a tree is also being pushed up by the branch. When the branch snaps, that upward push stops. The apple is suddenly completely free to follow the natural path through curved space-time. It instantly falls to the ground. But the apple isn't accelerating at all. The apple is finally moving naturally. You, standing on the ground, are being continuously accelerated upward by the floor. Falling is the most natural state. Standing still requires a force. That is the revolution of Einstein. 8. The extreme edge, from stars to deadly black holes. Once you understand gravity as geometry, extreme phenomena make sense. A star is essentially a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. What prevents its collapse? Pressure from nuclear fusion in the core pushes outward. It's a delicate balance. When the nuclear fuel runs out, the pressure drops. The balance is immediately broken. The star begins to collapse. If the star is large enough, it collapses until matter is incredibly compressed. Atomic nuclei merge. Electrons are crushed. What appears is an ultra-dense neutron star. Nuclear matter compressed to the size of a city. A single teaspoon of this stuff weighs billions of tons. For even larger stars, neutron pressure cannot prevent collapse. Space-time curves so sharply that every path leads inward. Not even light can escape. This is a black hole. Near a black hole, space-time is so warped that light itself spirals inward.
We cannot see black holes directly, but we see their effects. Matter falling into a black hole accelerates, heats up, and radiates enormous energy. 9. The ultimate beauty. Gravity is geometry. It all stems from one single idea. Mass curves space-time. Objects follow those curves. From this principle, everything follows. Planetary orbits, ocean tides, the precession of Mercury, a tiny effect Einstein predicted perfectly. Gravitational lensing and black holes. Gravitational waves. Ripples through space when massive objects collide. The principle that explains the moon also explains the largest structures. Galaxies. Gigantic galaxy clusters. It is universal and incredibly elegant. The pattern in the small piece reveals the design of the entire tapestry. Newton's equations work beautifully for practical purposes. We use them to launch satellites, calculate trajectories, and predict eclipses. They are simpler than Einstein's equations and accurate enough for most applications. But Einstein revealed what gravity truly is. Not a mysterious force pulling objects across empty space, but the curvature of space and time itself. Mass tells space how to curve. Curved space tells matter how to move. When you step on a scale, you are not measuring a downward pull. You are measuring the force the scale must exert to prevent you from following your natural path. When watching an object fall, you see matter moving freely according to the geometry that mass weaves. When looking at the moon, you see an object following the straightest path through curved space. The path looks circular because space itself is curved. Space brings objects together. That's what we call gravity. Not a force, but geometry. And that is far more beautiful than any mysterious pulling force. If you liked this video, you will definitely enjoy our next content. So, hit the subscribe button and turn on notifications so we can bring you more fascinating content in the next video.